Welcome back to the analysis of Sunshuttle. In part 1, we focused on the setting up of the program, which featured some light anti-VM, but also the reading and or creating of the configuration file. And now that we know how this part works, we can move on to the next function that was left for us, which was this main request session key here. And before we go in there, we notice that the return value is compared with 1, and depending on the results of this comparison, we can go into either this branch or this one. And in this branch, we see that we have a call to main random and then time.sleep. So the arguments for main random are here an integer of value 5. Let's rename this. And there, an integer of value 15. Like this. So if for some reason this main request session key function does not work, then we enter this block there and sleep for any number of seconds between 5 and 15. And otherwise, then we move on with the program. So now let's have a look at this main request session key, which is going to be the first attempt at communicating with the C2 server. Now, looking inside the function, well, we notice that it looks like stuff we've seen before. So I'm going to skip over the things that we recognize. So here we have this time hash, which appears to be a string. Let's change the type there. So creation of a few objects that we don't necessarily understand, but there we have creation of a get function with this net.htp.new request with context that we can, I guess, skip over. We have a refer here and there, and the creation of the headers. Let's move on here. Again, we see the same parameters as before, connection, keep alive. And here, something a little weird with values that we don't really understand. Add cookie. So this part there is probably going to be a cookie. This as well, probably, with here this value. This value here is a string, but if you look at the exact size, let me check, RCX is there, and RAX, actually, and oh yeah, it's here, is 3. So this value there is going to be this string, but only the 3 first characters, so 110. Anyway, cookie here, and then a user agent, which is the one that was obtained from the configuration file, etc., etc. And at the very end, we have this Nate HTTP client do. So, oh, and yeah, this time we see that we have references to conv I to I, and that most importantly, read all function, which means that for once, the return value is going to be used. So whatever is obtained from the C2 server this time is not going to be discarded, which was the case for the decoy requests. So now what we're going to need to do is to try to debug this program to figure out exactly what the requests look like and what types of parameters are being sent to the C2. But of course, as you can imagine now, all these C2 servers have either been seized, taken down, or sinkholed. And so it's going to be extremely difficult for us to obtain actual data that comes from them. So we could use a fake net here, which I guess would be efficient enough, but it's probably going to be a bit of a hassle to change the contents of the web pages every time we try to modify the return values from the C2. So what I propose we do instead is write our own C2 server with a simple Python script, for which I have provided a skeleton, which is going to help bootstrap your development efforts. And this C2 server, which we're going to be writing as we discover more about Sunshuttle, I think is going to help us a lot when figuring out exactly what the contents of the communications are. So what we're going to do first is we're going to modify the C2 server of Sunshuttle. And the way I'm going to do this is I'm going to open this with my hex editor. And I'm going to look for the C2 server as a text string. Now, I don't think we've seen it already, but if you do Control F and then HTTP, for instance. Oh, let me change this to text. Okay, then we get a few results. Let's look at this. Okay, actually, let's even look for HTTP : / like that. Not that many results. Let's try HTTPS. Okay, so it looks a bit better. So here cdn.mxpnl.com is a decoy URL, jQuery as well, etc., etc. Moving on, and we see more references to this nikeoutletinc.org. So had you looked at the strings of the program, you might have found those. Let me check a bit further. Yeah, we do see a number of these. And if you were to let the program run with FakeNet for a few minutes, then you'd see a lot of requests to this nikeoutletinc.org. Also, at this point, if you Google this domain name, that you'll see immediately that it's associated with this Sunshuttle malware, or more generally associated with the SolarWinds incident. So what we're going to do is we're going to replace this URL with another one that we control. And I'm going to do this by just replacing this text string inside the malware. So I know what you're going to say here, that it's not really the proper way of doing things, that we could set up a DNS server on the network that would reply 127.0.0.1 for all those requests. But I mean, this is going to take me only 5 seconds to do, and I think it's going to save us a bit of effort. One thing that you need to be careful about, though, is that in Go, strings have a fixed length, right? So we need to replace this with a URL that has the exact same length, but it's not going to be a problem. Another thing that we're going to be doing is downgrade this connection from HTTPS to HTTP, simply because we don't really want to bother with setting up any sort of SSL certificate and so on. The good news for us is if it were C code or C++ code, then usually the SSL handling would be performed explicitly in C, but here the Go library handles everything. So the user, the caller, just provides a URL, and then depending on the scheme detected in that URL, HTTP or HTTPS, then Go handles everything underneath. So we can just replace this with HTTP and move on with our lives. It's going to make things a bit easier. So let's redirect connection to localhost, port 8000, for instance. And now we see that we have a few extra characters left. So let's just add something like this. All right, so now the two URLs, the two domains have the exact same length. Let's just replace everything. So Control R, I believe, text, and we're going to replace everything there with this. And this is the URL we want to replace. So let's go replace all. And there we go. So I'm going to save this, close, and let's try running our simple skeleton C2 server and see if things work properly. At the moment, this Python script is just a simple HTTP server that is going to get all the cookies received in GET requests and print them. And it's also going to return a simple web page which contains the words "Hello World," and that's it. So let's try running this and see what happens. Okay. So now the C2 is running. Let's try launching the program that I have just modified. So yeah, you see, as expected, I do get an incoming request with a number of cookies here. Okay, so let's kill this program for now. If I can find it. Yeah, there it is. So now that we know that the C2 is working, or at least working enough for our purposes, we're going to try again in the debugger to see exactly where the various values are ending up. So let's go back here and put a breakpoint, I don't know, somewhere near the yeah, HTTP client do, or maybe even further, like in the read all there. Let's take this address, Control G, Control V, and yeah, let's put a breakpoint there and see if we hit it. And let's remove the other ones we might have created, and there we are. So here we see that probably this was one of our requests that was logged in the C2 server. And there, beautiful, we do have this hello world string that appears in there. Okay, so let's move on. We'll see that this is going to be converted to from bytes to string, spaces removed with the trim space function. Okay. And there probably there was a comparison here between hello world, the size of this string, and then a 0xa, which wasn't the correct value, right? Anyway, let's move on and see what happens. Return. And then we go back, we have this math random and then sleep. Okay, so let's see exactly why our request did not allow us to get out of this function. So here, oh yeah, you see that we have a test there, right? Let's check exactly what happens. So after this trim space function happens, we have this comparison with 0a, which is the size of the string, trim space, and then we compare whatever is in RCX with those values there, which sort of look like they are ASCII characters, right? Let's press R to convert them. And yeah, it appears to be the case. So the 8 first characters have to be those ones. Be careful though with the endianness, the string should actually be reversed. And then the 2 characters after this one are supposed to be U and then R. And the total is 8 plus 2, 10, which is 0a as expected here. So let's edit our script and return this value instead of the one that we are currently sending out, which is hello world. So let's replace this. Oopsie. Okay, so I'm going to reverse these characters. G, D, T, W, E, G, like this. And the 2 next ones are U, R, like that. So let's save. Control C, let's relaunch our C2 server and try again. So press F9 and we're going to hit our breakpoint again. And here you see that this time we have our expected string there. So let's skip over this. Now we have the comparison with the string size here. And you see that this time, yeah, the check is going to match. Jump is not taken. We compare those two. Supposedly, if I didn't make any typo, then we shouldn't have any problem there. And then we skip over here and return. And this time the return value is 1, right? So yeah, the jump isn't taken. So now we managed to reach this part there, supposedly. So let's skip over this. So we have one more random call and then time.sleep. And then there, depending on whether or not this configuration variable that we identified previously is 1 or 0, then we can create a new thread, I guess, in order to, yeah, new proc. And this here is the main false requesting. So probably we're going to skip over this because we do not have this flag enabled in our default configuration. So we just skip to here and then here, and this doesn't happen. So we skip over here and get into this main retrieve session key function. Let's see if I got things right here. So skip this. And yeah, main retrieve session key. So this time, let's skip over it and look at what happens in our C2 server. For now, I'm just going to copy everything here into my notepad so I can compare requests later on, because you see we have all these cookie values that are completely opaque for us. And the only way that we're ever going to figure things out is by, I guess, having a number of them and being able to differentiate. Yeah, this, by the way, 2BAC appears to be the idea that we generated for this backdoor previously, right? But we'll see. So let's skip over this function and step over it with F8 here. And now we have a new request here. Let's copy it and put it there and compare things. So this part appears to be fixed, this one as well, and this idea too. So the main difference between, let's say, main request session key, which I think was the name, and this main retrieve session key is going to be this cookie value there. So probably in our Python script, we're going to have to start and differentiate between the two types of requests. Let's go back to IDA Pro and now get into this function and try to understand what is happening in there. So again, we do have a creation of, let me change this type. Yeah. We have a creation of an HTTP object, sending of a number of parameters and headers. So this is not a GET request. The referrer. Okay, let's just skip over all this because I think it's pretty obvious that it's the same code that we've seen before, and find directly this read all. Okay, so this read all call there obtains whatever was sent by the server, and then it's converted into a string. I don't see any processing done on this. I assume that now we just kind of end the function and returned whatever was read there. So now we're going to go back to Python and write a little bit of code in order to differentiate between those two requests. So we'll need to return different responses depending on the cookie that we get. So let's check for it here. So this is the name. And first, let's try this one. So in that case, let's print a logging message. Like this, and keep returning this value here that was hard-coded in Sunshuttle. Otherwise, let's check for this value now. And if that's the case, then we can do some logging again, I guess. And it's not exactly clear what we should return there. We know it's probably based on name going to be a session key, but for now we don't know how it's going to be handled. So let's just put some random characters in there. And finally, if we're in none of these cases, then let's keep printing the cookies. Like this. And probably those headers should be sent before we start writing to the page, right? So let's put that block there, and I think we should be good to go. So let's start the C2 server again. Okay, and we are going to put a breakpoint into the function that we were looking at here in this read all call. So I'm going to copy the address again. Go back to the debugger, Control-G, Control-V, and put the breakpoint there. So let's press F9, there's going to be a bit of delay because we have all those 5 to 15 seconds random sleeps. So let's see what happens. Okay, so we got the session key retrieval request, and we hit here our readle functions. Let's pass F8. We get our triple, well, not triple, but our series of A's, and then convert it to here, a string. Let's go back to IDAPRO and see what happens. And then go to the end of the functions. Let's skip over everything. And we return after a bit. Okay, and here in RSP, we do have our function, our return value. In RAX, we'll have 1b, which I'm guessing is going to be the size of the string. And we'll see what corresponds to. So, going back here, we see that there are a number of possibilities, right? So the first one here is going into this block. So if here RAX is equal to this value, which I'm not sure what it is. Okay, let's ignore this for now. Then we can get into a block. We see that there are a number of tests there. Let's just see where we end up, okay? So skip over this, skip over this. Okay. And we end up here in this block. Let me just copy the address with Alt and then Insert. And then jump to it in IDAPRO, G and then Control V. And we end up there. And this is interesting, right? We see that we have some crypto happening. So SHA-256 being initialized, base64 decoding, and then some PKCS1 private key being created. So this is probably RSA, and there it's RSA decrypt OAEP. So this is where the fun stuff begins. Let's look at what happens there. Okay, so we see that our input from the C2 server gets moved around. That's fine. It gets base64 decoded, so we have to keep that in mind. We'll make sure to encode our input. And then here I think something quite interesting happens. Let's follow this in the dump. Okay, and we see that we do have a large number of bytes, which appear to be some base64. So let's copy this and look at what's inside. Let me open a new shell. Okay, and here, this looks like a private key, which is going to be used to decrypt data. Let's save that key to /tmp/privkey, I guess. And one thing that we're going to need, if we're ever going to be able to send data to the backdoor, is to get the associated public key, which is going to allow us to encrypt for this private key. I'm not exactly sure why the attackers chose to do things this way around. I think it would make more sense to have a public key inside the backdoor and then have the private key on the server to be able to make sure that only the server can send orders. But for some reason, they decided to do the thing the other way around. So in order to generate a public key, we can use OpenSSL, but OpenSSL is a bit finicky. So let's look at the key first. And I think for it to work, then we need to edit it a little bit and add RSA here and also at the end. RSA like this. Okay, and then OpenSSL RSA -in and then /tmp/privkey. Okay, it works. And -pub out. I think, okay. And here we have an RSA public key. Let's copy it, and we're going to need this. So let's put it there in our Python script. All right. Going back to ISAPRO, so we see that this key that was encoded as base64, this private key, is being decoded, and then it's being used probably to decrypt whatever was received from the C2 server. And the good thing for us is we have the associated public key, so we can encrypt data, and we also know the exact scheme. So we know it's RSA OAEP. So this is something we can do in Python. And then, depending on what happens, I guess this session key that we obtained from the C2 will be saved somewhere. So let's go back to our Python script and try to write some code that is going to allow us to send arbitrary data that gets properly decrypted. And this is going to happen here. So what we want is to have some sort of function. Here it will be RSA OAEP encrypt of this. So what would this function be? So let's create it above here. Like this, and it's actually pretty simple, but we're going to need a few more imports. I think it's this one, crypto.cipher. And then here, what we have to do is key equals, say that import key of RSA pub key like this. Cipher equals pkcs1 underscore oaep dot new, and then key like this, and then return cipher.encrypt data. Of course, this is not something I know by heart. I have the documentation pulled on another screen. And here, one very crucial thing is if you look up the documentation for Python's OAEP encryption functions, then you'll see that by default, the hashing algorithm it uses is SHA-1. And this is not going to sit well with Sunshuttle because if you recall correctly, I think we saw some SHA-256 happening a bit earlier. Let me try to find it again. I think it was at the top actually. Oh, no, right, I'm not in the correct function. Yes, I am. So here it is, SHA-256. So we need to make sure that we provide the correct algorithm for this. Equal SHA-256, that of course we're going to need to import. I think the parameter is actually hash algo. .256, like this. So hopefully if I didn't make any mistakes, then we should be able to obtain this string composed of A's at the end there. So let's stop my C2 server here and launch it again. Okay, no errors, which is actually some sort of miracle. Here, probably if I let the program run, it's going to crash because the decryption is not going to happen properly. Oh, but it looks like it doesn't. So let's wait for 15 seconds. And yeah, we reach this again. Oh, and I think I forgot something, right? Because now the data that we read, let's have a look at it. Hey, come on. Is probably not going to be base64 encrypted. I think I totally forgot to do this. Let's make sure, follow this in dump. It's a series of zeros and yeah, okay. It should be in here, so probably I need to adjust there. So let's import base64. and update the script there. Okay, this should be better. Let's make sure that this is the proper alphabet. Yeah, std encoding is the correct one. It's the only one that is used here, I think. So we should be fine. Okay, let's try this again. So again, let's kill the C2. Oh, and name RSA is not defined. Oh yeah. Here, let's do from crypto.public key. Yeah, import RSA like this. Okay. Now let's try again. So again, we have to wait for 5 to 15 seconds before we reach our breakpoint again. Okay, and there it is. So here we find something that I like a lot more. Let's follow this in dump, and yeah, this is some base 64, so all good. Let's actually remove the breakpoint there. Now I don't think we need it anymore. Let's execute until return. And we are back here just after our retrieve session key function. So let's put our new breakpoint there and skip over a few things. Okay, so we have this SHA-256 being created. So let's skip over it. So base64 decoding, which I don't think we are going to inspect the decoded value because it's probably just encrypted random data. And just skip over this because this is going to be the generation of the RSA cipher, parsing the private key. And here we have the decrypt function. So let's put the breakpoint there, remove the previous one, press F9, and hopefully things are going to work for us. So let's press F8. Oh, beautiful. And you see that here in RAX, I do end up with all my A's just as we intended. Okay, so let's go back to IDA Pro here. Let's skip over this. And here we have this decrypt OAEP. Okay, here in RCX, it appears that we have some sort of return value from decrypt OAEP, and RCX gets stored here. So let's go back to the debugger and make sure that this is the case. So let's see, RCX is going to be actually the size, and I guess, yeah, the decoded bytes will be in RDX. So RCX is here compared with this value. And let's see if we can find RDX somewhere. Yeah, okay, we'll find it eventually. So let's move on just a little bit. Okay, so conversion to string, okay. RCX is our string, 1B is still our size, and I'm going to copy this address here and see exactly where we are in IDA Pro. Okay, so this part here in RAX, we do have our size. So I think it's safe to assume, based on this function's name, that whatever is there is going to be a session key. So let's call this session key size. And probably this is going to be another string. So we know that we had a conversion from the bytes to a string. So let's just rename this session key and convert this to the correct type, like that. Right. And now if we go back, okay, so yeah, we do have here this size that is put in the session key, and then we copy the whatever was in the RCX, which was the data, into here, this data part of our session key. So far, so good. Let's move on in IDA-proof now and see what happens next. So it appears that if here this test is not satisfied, then we go all the way back up here, sleep for a bit, and then try everything again. So let's see what this comparison is. We have to check if RAX is equal to 0x20, and 20 is 32, which is like a very common number or very common size for keys. And if RAX, which is the size of our session key, is different from this, then we have to try again. So here we need to update our script and make sure that we actually provide a value that has the correct size. So let's do 10. Copy it, 10, 20, 30, and 2 more. So now things should be fine. Let's launch our C2 server again. Okay, and I'm going to, again, put our breakpoint where we stopped, press F9, and I think that we'll be back in no time. So having to wait between those requests is a bit annoying. I think if I were less lazy, I would just patch those actual constants, which were 5 and 15 to 0 and 1, but I'm not going to. So let's skip over this, and we have this comparison between RAX and 20, and this time, of course, RAX is the correct value. So let's move on. We have a sleep again. And meanwhile, let's go back to IDA Pro. So this is where we stopped. And then depending on whether or not we have the false requesting enabled, then we can either have this whole big structure again, which results in having this thread being created, or entirely skip over it, which is this red arrow here. Let's follow it. And then we will enter this main beaconing function. So let me just go there with the debugger as well to make sure that the two are synchronized. So F8. And here we are. So let me put this breakpoint here now, remove the previous one. And before we get into main beaconing, then it looks like whatever happens next in the malware is taking place in this function, because after this, we just loop back to the beginning and go back here. So this is the main loop of the program, I would say, where we have those sleeps, those random requests, if this is something that was required, and then interaction with the C2, and then we try again, and I think for the whole lifetime of the program. So I think this is a good time to stop this part as well. So I'm going to take a short break, and I'll see you again for part 3, which will be looking at the core of the malware, the actual interactions with the C2 server after the session keys have been established.